Good morning, everybody. Welcome to Tuesday morning, a Chem 1211 with your host, me, Dr. White. Hi. All right, here's the game plan for today. I'm going to go over some stuff, uh, that problems you should know how to do, and then we'll do today's lab. But before I do that, I want to mention, got an email from one of your colleagues, uh, about the lab that's due today and had a problem with the calculations. And your colleague obviously made a math error. This is the one with the rings. Follow what I have in my video. Let's see if I can find it. Let's make sure you can see it. Good morning, everybody. Oh, sounds familiar. All right, now if you go to this video and you go to about right around here, and that's 1:11:07, 1 hour, 11 minutes, and 7 seconds. You'll see I describe how to use this formula. Don't forget, I haven't finished yet. Oh, that looks professional. Anyways, and how to use this formula. And what I will tell you is with the student's data that she sent me, I set up a spreadsheet. I know how to use spreadsheets. I've been using them, wow, I don't know how many decades. Yes, decades. And I found out her data, oh, is that good? Blueberry tea. But anyways, her data, when I did the calculations, was pretty close. Considering the expensive calorimeter you're not using, the theoretical value or the actual value, literature value is a better name for it, was 0.50. And with her data to two significant figures, I got 0.60. Considering the equipment and the student, you haven't done this before, that's quite good. So the experiment works, but you got to do the right calculations. And if you have any problems, come to my office hours tonight at 6 to 7:15 and tomorrow night from 6 to 7:15. And for this lab, you handed in a little late. Shh, don't tell the instructor I'm being nice. Okay. Shh. But anyways, I won't take off points if you have to come to my office hour for help with the calculations. All right. Now, let's go through. I found out that I had already done, at least I believe I did, Chapter 10, Part 2 problem set. So what I like to do is a couple from there, in the sense when I say from there, that we didn't do. All right, let's go through how do you draw the Lewis structure for oxygen gas? Well, Lewis structure means the valence electrons, the outermost. So the first thing we have to do is find out how many valence electrons does oxygen have in O2 oxygen gas. And how do you do that? You look at your friendly neighborhood periodic table. Does everybody thumbs up, people? Do you see the periodic table on your screen right now? Uh-oh, I better check. You should see it. All right, I'm assuming you do see it. And if you look on here on the periodic table, if you look above oxygen, you'll see the number 6. That means oxygen has 6 valence electrons. So we have oxygen with 6 valence electrons. And if we draw the Lewis structure for each oxygen atom, remember, dot on one side before pairing up for elements. That's not true for molecules. So this oxygen says, oh, I've got 2 unpaired electrons. Let me use a different color, not to confuse you. I've got 2 unpaired electrons. You've got 2 unpaired electrons. Let's share. And they do. And the non-bonding electrons come along for the ride. And here's the answer you would do. Now, next question I would ask, what kind of covalent bond exists in oxygen gas? And notice right here, how many pairs of electrons? 2 pairs. And what kind of bond is that? A double bond. And why don't you try this one on your own? Then I'll do it. Carbon dioxide, that's the bubbles in pop or champagne or beer, or when you burp, most of the gas coming out with your burp, or a good amount of it, is carbon dioxide, CO2. Now, first of all, to do the Lewis structure of CO2, you have to do what? Find out how many valence electrons carbon and oxygen have. Well, carbon over here on the periodic table, look at the top, you see 4 valence electrons. Nitrogen, we're not doing that one, oxygen has 6. So carbon has 4 valence electrons, oxygen has 6 valence electrons. And why don't you try drawing the Lewis structure for carbon dioxide, CO2? Remember, you're supposed to be drawing the Lewis structure for carbon dioxide, CO2. Oh, hint, the only way you could make this work if it's carbons in the center. And when you're done, give me a thumbs up. All right. Looks like everybody's done, so I better get to work. All right, how do we do this? Well, carbon has 4 valence electrons. Oxygen has 6. Now, each oxygen, because there are going to be 2 of them here, looks over at the carbon and says, huh, this oxygen says, I've got 2 single electrons. Carbon, you have, let's share. And they do. And the valence non-bonding electrons come along for the ride. Now there are 2 of these. So the other oxygen says, oh, you've got 2 left. I've got 2. Let's share. And they do. Now, I didn't mention up here, but all atoms except for hydrogen, when they're in a covalent bond, want to have 8 valence electrons. So if we look at all the shared and non-shared electrons in that oxygen, 2, 4, 6, 8. Same thing here. Now, if we look at carbon, in the blue, 2, 4, 6, 8. If we come up here, that each oxygen will have 8 electrons. So that's the beauty or the importance of the octet rule. Remember, in a covalent bond or any bond, atoms gain, lose, or share electrons to have 8 valence electrons. Now, let's do one more that I'll do. Then I'd ask you to try this on your own. And let's do the valence electron, draw the Lewis structure for this compound. It's called potassium hydroxide. And it's an important chemical used in the chemical industry. Later on, I'll teach you it's a very strong, what we call a base. So how do we do this? Well, we've got potassium, oxygen, hydrogen. Now, I've already done, well, let's go look at the periodic table. Hydrogen has 1 valence electron, oxygen still has 6, and then potassium has 1 valence electron. However, except for hydrogen, which is not really an alkali metals, the alkali metals and the alkaline earth metals never form covalent bonds. They don't. They lose electrons to form cations, and potassium, like sodium and lithium, loses 1 electron to get to the nearest noble gas and will have a plus charge. So let's take a look at this. This will always form this and lose 1 electron. Oxygen has 6 valence electrons. Hydrogen has 1 valence electron. So if I have my oxygen here, and I have my hydrogen, this has 1 valence electron. Hydrogen has 1. There's now a single bond. 1 pair of electrons between the oxygen and hydrogen. Now, potassium will be this cation. But if you look at oxygen, count the dots, there are only 2, 4, 6, 7. That's not an octet. But where does this electron that potassium loses? It goes over to this oxygen. It now has an extra electron, so it has a minus charge. And between the potassium and this is called the hydroxide anion actually. I guess it's really ion. And there's a ionic bond between the oxygen and hydrogen. There's a covalent bond. All right, that's what I wanted to go over that. And there's another thing I want to cover again, because repetition is good for your grade. I also get what I want. You learn the material. All right, let's go through a few more things. Remember, we did balanced chemical equations. Let's look at the following chemical equation. And I will ask you, and then I'll do it, balance that chemical equation. And remember, on test one coming up in a week or so, I will be, not next week, the following week, I will be asking you to do balanced chemical equations. There'll be at least 3, possibly 4, which means 9 or 12 points, because these are 3 points each. And give me a thumbs up when you balanced it. Oh, remember my advice, leave hydrogen, oxygen last. All right, my turn. Now, I'm going to follow my advice, not do hydrogen, and say there's 2 nitrogen on this side. Ooh, there's 3 here, or 1 here. I'm looking at the wrong one. How do I get it to 2? I can't change the formula, but I can put a 2 there. So now I have 2 nitrogen, but how many hydrogen? 2 times 3 is 6 hydrogen. How do I get to 6 hydrogen on this side? Well, I've got 2, and 2 goes into 6 3 times. So now I have 6 hydrogen. And so I'll check 6 hydrogen, 6 hydrogen, 2 nitrogen, 2 nitrogen. And that's how you balance this. Later in the semester, I'll talk about this specific reaction, which 2 Germans were able to uh, make work in chemical plants. And those German chemists were Haber and Bosch. And this little reaction, once they were able to make ammonia, NH3, changed our world. It did. This happened about 1905, 1910. Well, a little over 100 years ago. All right, let's use that balanced chemical equation. I will never ask you to balance a chemical equation for the following type of problem. All right, let's read the problem. How many moles hydrogen gas, H2, are needed to make 4.138 times 10 to the third power moles of ammonia? And let's do this stepwise. The first step I would ask you is, what are you being asked to find and what are you given? So why don't you do that? And then I'll do it. Once you give me a thumbs up, you're done. Again, I'm not asking you to do the whole problem. This is what are you being asked to find and what are you given? Once you figure out, all right, time for me to get to work again. So what are we being asked to find? How many moles of hydrogen? So we're trying to find moles of hydrogen. What are we given? Well, we're trying to make these many moles of ammonia, NH3. And we're also given this balanced chemical equation. That's important too. So let me rewrite it again. So how do I continue? Hold on. Nope, it's not the Secretary General of the UN or the President of the United States. I'm not going to answer it. It's sorry about that. That should be the last one, I hope. And now my voicemail will pick that up. All right. Next, what units are you trying to get to? This is all we have to have. Well, we have to work with. Over here, why don't you figure out what units you want your answer to be in? When you've done that, give me a thumbs up. And the answer is moles of hydrogen. Now, if we had a ratio that we could convert this moles of ammonia to moles of hydrogen, your turn. What units go on top and below that ratio? I'm not asking for numbers, just the units that go on top and below that ratio. Don't forget to use your good friend, your good buddy. And when you figure this, the units, give me a thumbs up. All right, it's my turn. And guess what time it is? It's time to use your good buddy, your good friend, unit analysis. I love my whistle. Company that made that is from West Germany. They went out of business years ago. And that one, I have 3 others, never leave my house. All right, using unit analysis, whatever we're trying to get to goes on top of that ratio. Whatever units we don't want in our answer goes underneath. I'll write those. And now where do we get those numbers? From the balanced chemical equation. The coefficients, the number in front, give us molar ratios. When there's no number, it's the number one. So what this really tells us is 3 moles of hydrogen react with 1 mole of nitrogen to make 2 moles of ammonia. Again, 3 moles, the coefficient tells you molar ratios. 3 moles of hydrogen, so I can write the 3 in there, react with 1 mole of nitrogen, we don't have that in our, to make 2 moles of ammonia. So I can put that there. Remember, this means moles. Remember, moles are the chemist counting unit. Now, before I pick up my calculator, which is over here, over that way, you can't see it, I'm going to check. Notice moles of NH3 divided by moles of NH3. And anything divided by itself equals the number 1 because it cancels out. So that cancels out. I'm left with moles of hydrogen, which is what I'm trying to find. So now I can pick up my calculator and turn it on, clear it, 4.138. And then for this calculator, second key, double E, and I have 3 10 to the third times 3 divided by 2. And my calculator gives me this answer. Now, when you're doing multiplication and division, you get the same number of significant figures in your answer as the number that has the fewest significant figures. Now, if we look here, that has all non-zero numbers are significant, 1, 2, 3, 4, 4 significant figures. Now, these numbers here, 3 and 2, come from the balanced chemical equation, and those are exact numbers. And they're never used to determine significant figures. So the only thing I have to go by is this should be, my answer should be 4 significant figures. Luckily, my calculator gave me 1, 2, 3, 4. And so this is the answer. I'm done. And let's go through this again. We found out from the how many moles hydrogen are needed to make 4.138 times 10 to the third moles of ammonia, NH3. We're trying to find moles of hydrogen. We're given how many moles of ammonia. We're also given this balanced chemical equation. And next, this is the only number we have to start with. This is the units we're trying to get to. And then follow the red arrows because you're using your good buddy, your good friend, unit analysis. Whatever you're trying to get to, answer-wise, goes on top of the ratio, moles of hydrogen. Whatever we're trying to get rid of, the moles of ammonia we don't want in our answer, goes underneath the ratio on the bottom. And where do we get the numbers? From the balanced chemical equation. The coefficient, the number in front, tells you how many moles. And this tells me for this balanced equation, 3 moles of hydrogen react with 1 mole of nitrogen to make 2 moles of ammonia NH3. And therefore, where do I get a relationship between moles of ammonia and moles of hydrogen? Well, right from the balanced chemical equation. 3 moles of hydrogen, H2, makes 2 moles of ammonia, NH3. And I do the math and I got the number. And that's how you do that. And we'll do more tomorrow. If I look at the clock, we're right on time. All right, that's today's work with material from the lecture, and it's lab time. And as I mentioned yesterday, we'll get out early today, which is sometimes a good thing, but we'll cover everything we need to cover. Excuse me. But anyways, as I mentioned yesterday, the full-time faculty member who got a really good kit this semester, I'm really impressed with the Carolina chemistry kit. It's a great improvement from what we used 2 summers ago, which was, I'll be polite, stunk. Actually, it double stunk. Oh, it was awful. But this kit is doing a good job. Unfortunately, with the kit that was purchased, there are only, I think, 12 labs available. But normally when we do face-to-face on campus for 1211, we do 14 labs. So luckily, I know how to write my own labs, and stuff we've done that weren't included in the kit, I can put in and write my own lab. The only thing is you can't do the actual lab part. So I put in the data for the 2 I'll have you do from Dr. White. And today is one of those days. All right, thumbs up, people. Do you see calorie in a nut? All right. Now, have you ever, let me stop share for a second. And I thought I'd go healthy on you instead of bringing some candy. Dr. White loves tuna. This is good stuff from Costco. Not that I get any money from Costco. And if you look on the back, you'll see right here, it says 180 calories per serving. And as you learned from the last lab, that's a measure of heat, energy. And also, this can be converted into things in your body like weight, which is why you keep an eye on the calories. And why are all the good things super higher than this, like potato chips and other things? I don't know. But how did they get that number? Well, they measured heat given off when it's burned. And today's lab is called Calorie in a Nut. Now, we also do the same lab for the equivalent course to 1211 at Elgin Community College. And a number of years ago, right before we were going to do this Calorie Nut lab, there was a lot of news reports in the news about students who were having severe peanut allergies. And it dawned on me, I asked my class, because next week we were going to do this calorie of a nut where you burn it and the whole room gets filled with smoke with some of the different chemicals from a nut. And I asked, anybody here have nut allergies? Because I saw about that in the news. It's been. And I had 2 students raise their hand. So I went and talked to the other faculty and said, we got to do something different. And turned out we came up with using corn chips, and you can also use potato chips. You'd be amazed how well those burn and how well nuts burn. I mean, it's amazing. Now, let's go back and look at the lab. And heat is a measure of energy. One scale is calories. And you've seen different foods have different calories, energy. In today's lab, and since we're just doing it theoretically, we'll use a peanut or a nut, but normally we would have used it. In the nut, there's certain chemicals called fats and oils. And if you take my Chem 1212 here, or I also teach Chem 170, both are organic at Elgin Community College, you'll learn about fats and oils. And when this reacts with oxygen, it burns and gives off heat. And you can collect the heat by putting it over a container of water. And you measure, just like you did last week, the difference in the final from the starting, and we call that delta T. And you can calculate the heat given off by the nut, and therefore the heat in calories. In this lab, we'll use calories, not joules, which is another heat scale in a nut. Now, this is called calorimetry, and the calorimeters, like the one you didn't use last week, can be very expensive and accurate. And they can cost, like I said last week, up to tens of thousands of dollars. Now, for this lab, and I'll show you the video in a second, you use an empty pop can that you, as your calorimeter, you fill it with water, and underneath you burn the nut, and you measure the delta T. Now, for using calories, we use the heat capacity of water of 1. It takes 1 calorie to raise the heat of 1 gram of water 1 degree C. And you'll calculate that. And you'll see how Dr. White writes the lab. All right. Sorry, but we're going to have to get this commercial out of the
If you're
way.
going back to school, before you submit your essays, run it through Grammarly to quickly check for spelling, punctuation.
I'm going to be conducting.
All right. Does everybody see the pop can on your screen and the woman who's about, thank you. All right. Now, at ECC, we do it a little differently, but similar. We do something similar we have in the past. I think at COD, we use bread now.
In the calorimetry lab with a peanut. The first thing you need to do is read through your lab and then make sure that your setup looks like mine does here. Make sure also that your stick for the food source is measured out as being only 3 centimeters away from the base of your can. So make sure to measure that. You're going to need 100 milliliters of water that you will pour into your can. The water temperature is what you will be recording initially and then after the food source has burned. Go ahead and place a thermometer into the can and let the thermometer adjust to the temperature. While it adjusts, I'm going to take the mass of my food source, which is a peanut. The mass of my peanut is 0.5 grams. You need to record that into your data table. The temperature of the water in my can is 24 degrees Celsius. Very carefully place your food source onto the pin.
We developed a better
and then you need to start your food source on fire. I'm going to use a candle to do this because it does take some time to start the food source burning.
We use a gas lighter.
Be very careful with matches.
If she held the flame down a little lower, it would start
Once the
quicker.
food source is caught on fire and is burning, I will go ahead and place it under the can with the water in it so that the temperature change can be recorded. You'll start to hear some little kind of clicking when it starts to burn. That is a little indication to you, like kind of popping, that the food source is on fire on its own. You're going to let that burn and heat up the water. Now that the peanut is completely burnt, you're going to check your ending temperature on your thermometer. For the data for the peanut, you're going to record a temperature of 33.5 degrees Celsius. You will be conducting this lab with 3 other food sources.
Did you know luxury hair repair doesn't have to cost $50?
All right, let me say, listen carefully. You won't be doing that at home. Let me say it again. You will not be doing that at home. I will be giving you the data. Do not burn anything in your home. So let's look at the lab. Now, I also have a way of doing calculations. Now, let's look, and you'll use the formula A. Does everybody see formula A here? Do you see it right here? All right, that's the formula. Now, your calories of your nut will be the mass of the water in kilograms. I'll explain this in a little while, times the change in temperature, delta T, times the specific heat of water. And the specific heat of water, notice I have in red, 1.00 calories per kilogram degrees C. Now, you'll be also asked to measure, like I say on the label, how many calories per gram your nut is. So let's look at the calculations. If you were going to do the experiment, which you're not, you do not do this. I think I'll, before it later today, this is not what you're going to do. Now, here's the mass of the water. If you had done it, it's in red. Notice the delta final initial temperature. Over here, everything in red, you either have to use or calculate and use later. How do you calculate delta T? Number 1 minus number 2. Now, here I give you the weight of the nut and holder. Here's the weight of the residue after you burn it with the holder. And you have to find number 5, which is the difference of 3 minus 4. And that's the weight of the nut consumed, number 5. Now, to determine the calories in your nut, you'll use formula A. And formula A, note, number 6, that's this, you'll use the values in red. Here's the mass of the water, here's the delta T that you'll calculate, and here's the calories. So mass that you'll calculate in kilogram, which I give you, delta T you have to, and here's the specific heat of water. You'll do this calculation, and that is number 6. Now, your calories per gram in your nut is number 6 divided by number 5. And I have some questions for you to answer. And here, we actually did this in real life before at ECC, before we switched from peanuts to corn chips, both burn real good. You should, first time I did this lab, I was shocked how big the flame was coming from peanuts. And later on, same thing with corn chips, but they have a lot of oil in them and fat. Now, on the can of Planters peanuts, it says it's 5.71 calories per gram. And I asked you to compare it, and then what's your source? Now, once again, you're not going to do any experiment at home. You will not, no, do not burn any nuts or anything else for this lab. You'll use the data I gave you to do the calculations, and that's today's lab. And if we look at the clock, I've done everything I wanted to do today. Today's a shorter lab day. Sometimes they are like that. We did some good practice, and I went through the lab. You'll do. Remember, do not, no, don't burn anything at home. You'll just use the data I give you. With that, I'm done. And don't forget tonight, I have my office hour from 6 to 7:15. If you need any help with anything, please stop on by. With that, I'm going to say, gang gesund, goodbye. Have a nice day. I'll see you tomorrow or tonight. By the way, I stole this from Granny at the Beverly Hillbillies. Gang gesund. Bye now.